Hey guys, got another set of example problems here. Today we'll be looking at actual mechanical advantage. Actual mechanical advantage is measured with force, not distance, but the equation is very similar to the IMA equation, in shape anyway. So let's take a look at these example problems. We'll be doing these in the exact same way as before. We'll use in the same problem-solving process. So we'll read it, and then we'll make a list, write an equation, rearrange, plug in and solve. Okay, so we're calculating the effort force that is needed to lift a 50.4 pound load with a lever if the AMA is 3.41 to 1. Before we do anything, let me remind you that the AMA equation, actual mechanical advantage, is equal to FR divided by FE. Now, this is different than the IMA equation. The IMA equation has dE divided by dR. And you might be wondering, why is it backwards? Why is the R on top here and the E is on top here? Well, that's actually really easy to explain. With actual mechanical advantage, we're talking about forces. When we talk about advantage, you have advantage when you apply less force than what the object weighs or whatever your resistance is. So if your denominator number is less than your numerator, then you will always have a mechanical advantage that's greater than 1. With IMA, the further out your distance effort is, the more leverage you have, the more mechanical advantage you have. So it's a very easy and common mistake to put E on top for this equation, but just try to keep them separated. Anyway, let's go ahead and make our list. So for this problem, we are looking for effort force. So that's FE. And we are lifting a 50.4 pound load. And I used this word because this word is commonly used to represent FR, our resistance force, whatever it is that we are lifting. And that is 50.4 pounds. And our AMA is given as 3.41 to 1. And just remember that this is the notation that we use for mechanical advantage. It's a ratio. It's not part of the number. It's just like feet or inches. It's a unit. Okay, so in this case, we are looking for effort force, FE. We're looking for effort force. Now, if you watched the video about ideal mechanical advantage, then you know that I have a trick for getting this number out of the denominator. So what I'm going to do is I'm going to take these two variables and I'm just going to flip them around. This is the Mr. Adams' lazy math trick. So if I rewrite my equation, that is FE is equal to FR divided by AMA. Remember, the only thing that's important here is that we do not move the numerator. The numerator stays put. Everything else moves. If you don't believe me, you can do it the long way and you'll get the same thing. Okay, so let's go ahead and plug in. So this is going to be 50.4 pounds divided by 3.41 to 1. So 50.4 divided by 3.41 gives me 14.78 and a bunch of zeros. So we are going to go ahead and round that to 14.8. And our units are going to be pounds. So our effort force is 14.8 pounds. All right, let's take a look at the second problem. The second problem is asking us to calculate the load of a simple machine if the AMA is 2.89 to 1 and the effort applied is 410 pounds. So let's go ahead and make our list. First thing that we're given is that we're looking for the load. Remember, load is a word that's used to represent FR. AMA is 2.89 to 1. And we are told that the effort applied is 410 pounds. So that's our effort force. Okay, just like always, our next step is to write our starting equation. AMA equals FR, not E, FR divided by FE. So for this problem, we're looking for resistance force, which means that we are looking for the numerator of this equation. So we need to get FR by itself. To get FR by itself, we have to get rid of FE. FE is being divided, so we multiply. So FE times AMA over here, the FE's over here are going to go away. If we rewrite our equation, we get FR equals FE times AMA. We know both of those things, so we can just plug straight in. So our effort force is 410 pounds, and our AMA is 2.89 to 1. So 410 times 2.89 is a big old number. So we get 1184.9, which if we round to 3 digits gives us 1180. So just about 1,200 pounds of force. So I only have 2 example problems written here, but I do want to do one last problem. Let's say that our machine from the previous problem has an AMA still of 2.89 to 1, but its ideal mechanical advantage was calculated to be 3.2 to 1. If that's the case, how efficient is the machine? Well, our efficiency equation is %E equals actual divided by ideal times 100. And the reason that we're doing the times 100 is because we are calculating a fraction and then we're going to multiply it by 100 to turn that fraction into a percent. In this case, we don't need to rearrange anything, so we can just plug in. So 2.89 divided by 3.2. Now, this is where I see a lot of people make mistakes. Where I see people calculate that machines have efficiencies of 120%. If that's the case, the most likely explanation is that you have goofed these 2 numbers up and that you've put the IMA on top. Most times, AMA will be less than IMA. And the reason that I say most times is, let's say that you do an experiment and you collect some measurements. It's entirely possible that you could get that your actual mechanical advantage was greater than your ideal mechanical advantage. And if that happens to you, that means that you have made some sort of a measurement error, or that you measured your distances wrong. It's impossible for a machine to be even 100% efficient. There's always loss of efficiency due to heat, friction, experimental measurement, etc. Most vehicles are incredibly inefficient, as an example. So most cars are between 18 and 20% efficient, if you can believe it. Anyway, let's go ahead and plug this into our calculator. So 2.89 divided by 3.2, and then I get 0.903125, but I'm going to multiply that by the 100, and that will turn that into an efficiency of 90.3125, which we will round to the 10th place there, 90.3%. That is pretty darn good for our machine. Okay, we will go ahead and stop there. In class, we will continue to work on these calculations and get better. I'll see you in the next video.